Greetings. I am very sorry that I couldn't make it to class yesterday, but I wasn't feeling very well. So, at any rate, hopefully we're not going to have to do too many of these remote lectures. So, let's get started. Last week you guys had your first exam, so I wanted to comment on the exam a little bit. As you can see, the average was quite high, 83%. The median was 85. That means half of the class scored at an 85 and higher, and half of the class scored at less than 85. So if you're thinking about grading as a straight percentage, this basically is saying that at this point in time, half of the class is getting a solid B or higher, and then I don't feel uncomfortable saying that grading straight percentage is likely the way we're going to be for this course as it's stated in the syllabus. All right. I did want to just mention there were a few folks in this region of the mid 60s to low 70s. I'd really like to see their performance improve on the second exam. So whatever you're doing, you might want to amp it up a little bit in order to do a little bit better in the future. And then there were a few students that scored less than 60, right? And I will be honest with you, that's far away from the pack. In order to be successful in this class, you're gonna really have to ramp it up a little bit, a lot, in fact, right? The other thing to keep in mind is that if you're getting low scores like 60 or less, then it really does tell us that you didn't learn the first quarter of the semester's material, and this subject matter is hierarchical. So in moving forward, you're going to have to work harder, but you're also going to have to learn what you didn't cover in the first quarter. So if you fall into any of those camps, or if anybody would like to talk about how they might do a little bit better on the next exam, please don't hesitate to get in touch with me. All right. Okay, so a few reminders. There's a quiz on Canvas that's required, that's due today, just shy of midnight. If you didn't get an opportunity to look over your exam, you can stop by my office hours or during the TA office hours. And just wanted to remind everybody that these exams are secure, so you can't take notes on exam content, you can't take photos, and you can't take the exams with you. Violating these rules is a violation of academic misconduct, right? And then the deadline for requesting a regrade on the exam is next Tuesday. So as with everything that's graded in this course, there's a 2-week turnaround on requests for regrades. So sort of summarizing where we've been, some things that we've talked about previously. We've previously pointed out a fundamental theorem in physical chemistry. That is, when we use the probability distribution for an ensemble of systems using partition functions and Boltzmann factors, we expect that that average will be the same as what is experimentally observed macroscopically. And that, of course, gives us a lot of power in connecting the microscopic or quantum mechanical domain with macroscopic laws of thermodynamics. So once we introduced the partition function, we were able to manipulate it first to show that, let me take this step by step. So this first term here is the summation of the energy of a system in an ensemble times the probability of a system being in a particular energy state. All right? So that's just straight up statistics. If I know the probability of being in some state, the value of that state summed over all of the possible states gives me the average value. We showed that this statistical form is exactly the same as the negative of the derivative of the natural log of the system partition function with respect to beta, right? And that basically tells us that if we have an analytical function for system partition function, we can always determine the average value. right? And we've seen some examples of that, and we'll see some in a moment. We also pointed out that sometimes we'd rather work in the temperature domain rather than the domain of beta. So we derive the expression for energy in terms of temperature, and then we have kBT squared times the partial of the natural log of the system partition function with respect to the temperature. All right, so once we introduced those equations, what we were able to do was apply them. So in chapter 4, we'll derive where the partition functions come from, but what we've stated and what we're about to show is that the system partition function is given by the particle partition function raised to the n, where n's the number of particles, over n factorial. And this expression, as we'll see today, is used when you have identical and indistinguishable particles. All right, so given the expression that relates system partition functions to the partition functions of the particles, then we need an expression for the partition function of the particles. And again, in chapter 4, we'll derive this, but for a monoatomic ideal gas, which has only translational energies allowed, we are giving this expression. All right, and what I can do then is I can take that Q, plug it into our little q to the n over n factorial, and then take the derivative of the natural log of it with respect to beta. And what resulted for that was the average energy of our system, which consists of monoatomic ideal gas particles, right? And that was 3/2 RT, right? From there, we moved to our discussion to talking about diatomic ideal gases, and to reference this a little bit, what we know from chapter 1 is that in describing the energy of an ideal gas, we can talk about the translational energy, the rotational energy, the vibrational energy, and the 0-point vibrational energy. And putting that all together, again, we have a particle partition function, little q, which is broken up into parts, or may be broken up into parts, where I have my translational portion, I have a rotational portion, and the last portion is the vibrational. All right, and again, once I have q, I can take the derivative of the natural log of q over n factorial with respect to beta, and that will get me my average energy. All right, and what we showed was that gives us 3/2 RT, that's our translational or kinetic energy, RT, which is our rotational energy, NA H nu over 2, which is the 0-point vibrational energy, and then the final term is the vibrational energy above the 0 point. All right. So from there, we also introduced heat capacity at constant volume, and what we've defined it as is the change in the energy of the system due to a change in temperature. All right. And so that basically says that the energies that we have just calculated just need to have the derivatives of them taken with respect to temperature, and that gives us the constant volume heat capacity. So for a monoatomic ideal gas, we found that to be 3/2 R, right? And again, because the only energies that are available to our monoatomic ideal gas are translational, that means that when we change the energy of the system by raising or lowering the temperature, the impact is on the kinetic energy of the particles. For a diatomic gas, that's a little bit more complicated, but again, we take our energy, take the derivative of the energy with respect to T. That gives us a translational contribution, a rotational contribution, and a vibrational contribution. And basically what this says is that my system, if I change the temperature, some of that energy change will go into translations, some of it will go into rotations, and some of it will go into vibrations. And then we took a little bit of time to focus on the vibrational contribution to the heat capacity. And we basically found this expression, the molar heat capacity is given by this expression. If we talk about looking at this at the low temperature limit, we find that this heat capacity goes to 0. At the other extreme, this is called the classical limit. So as temperatures get really, really large, we find that the limiting value of the heat capacity contribution to vibrations is R. And this will be R for each vibrational degree of freedom. All right. And then the other thing that we did was we went back to statistical mechanics, and we basically said, well, if we're interested in knowing what the pressure is experimentally, I can talk about having my systems in an ensemble. So I can say, here's the probability of a system being in a particular quantum state, and then we have an expression for the pressure of that particular quantum state. So we needed to introduce the fact that we will later show where this comes from, that the pressure of a system is given by the negative of the change of the energy of that system caused by a change in the volume. And by manipulating the partition function, we show that that's the same as kBt times the partial of the natural log of Q with respect to volume. And what you saw in the course of the homework that was due on Friday is that this allows you to calculate equations of state or predict equations of state from partition functions. So that, again, extends great significance to the power of statistical mechanics. Right. Our next task was to ask the question, where does the expression come from relating our system partition function, capital Q, to our particle partition function, little q? And what we showed previously is that if we're talking about independent particles that are distinguishable from each other, we find that the system partition function is the particle partition function raised to the nth power, where n's the number of particles. All right? And that allows us to define a system partition function separate from a molecular partition function. And it's basically the summation of the Boltzmann factors. If I'm talking about the system partition function, it's the Boltzmann factors of the energies of systems in quantum states. And if I'm talking about a particle or molecular partition function, then the energy is the energy of the particle that makes up a system. So at this point, we've shown that Q equals Q to the n for distinguishable identical particles. Now previously we've used Q equals Q to the n over n factorial. So we need to see where that comes from. All right, so that's one goal for today. Then once we have this relationship established, then we can talk about using Q for our particles to determine the energy on average of particles. Up to this point, we've been talking about energies of systems. And what we will see is that when we can determine the energy of an individual particle, we'll be able to talk about translational, rotational, vibrational, electronic energies for the particles that make up the system. All right? And then from there, and I'm not sure that we're going to get there today, but then we'll go into Math Chapter C, where we'll talk about Maclaurin series. All right, so we are going to start today on page 16. So we had a lecture quiz that covered this relationship. So I'm going to say see Wednesday's lecture notes. Because the lecture quiz that we gave on Wednesday was really designed to demonstrate this portion. What we can do now is we can talk about the outcome of that. Right? So if I have independent distinguishable particles then I can say that my system partition function is given by the partition function, which is a function of v and beta for one of my particles, times the particle partition function for another particle, v beta, times qc, where c is my third particle, v beta, all the way out to my nth particle. And then we can say, what's this little q? Well, qi is then the summation of Boltzmann factors, e to the minus beta, and now we have an energy that's associated with the particle itself. All right? So the equation that I've written here for the system partition function is absolutely general. It's for any independent and distinguishable particles. Now, if I have particles that are independent but also identical, I would expect that QA and QB and QC are all equal to each other. And if that's the case, then we can say that our system partition function is Q, function of V and beta, raised to the n power. All right, and then the next question is, when are these particles distinguishable? So if I have, say, two water molecules that have the same mass, and I put them both behind my back and I pull one out, there's no way for you to determine which one of them it is. So they're indistinguishable, all right? So that also tells me that if we're talking about a gas, where I have a container with, say, 10 molecules in it, if the 10 molecules are all identical, if I point to one, there's no way for you to say that's different than another one. So they're not distinguishable. Things are distinguishable whenever they're identical if you can somehow label them. And the easiest way to do that from this, in this construct, is to be in the solid state. So in the solid state, identical particles are distinguishable by position. So that really tells me that if I am talking about the solid phase, I will use the expression capital Q, system partition function, is given by Q to the n, where little q is the particle partition function, right? But that also tells me that this is not going to work if I'm talking about the liquid or the gas phase, all right? And so what that means that we need to do is then we need to think about Q, system partition function, for indistinguishable particles. All right, so again, we're going to start with this construct of having a two-state, two-particle system. So I have 1, 2, state 1, state 2, state 1, state 2. I'll have particle A, particle B. I can have both my particles in the lower state. I can have particle A in the lower state, particle B in the upper state, and the last possibility that's unique is to have both particles in the upper states. Right? And so if we have a system of two particles with two levels, that basically says that my system can have 4 different energy states. Both particles in the lowest energy state, both particles in the highest energy state, and then one particle up and one particle down. All right? So we've talked about this kind of thing before. All right? But now we need to look at this a little bit more closely. All right, so you may recall from back in general chemistry, you were told that no two electrons could have the same set of quantum numbers in the same atom. And basically another way to say that is to say that you can't have multiple particles in the same identical quantum state as another. And that holds true when we're talking about things like electrons and fermions. So if we're talking about systems that consist of fermions, that means that I'm not allowed to have state E1 and E1 or E2 and E2. Right? So those aren't permissible. So I only am permitted these two other states. Right? Now the reason for mentioning this is basically that we can simply state that what we've previously derived, that is our system partition function being equal to the particle partition function raised to the nth power, cannot be true for fermions. All right, and then there's another thing that we need to worry about, all right? And this is something that is solely because of the strangeness of quantum mechanics, all right? But if I have a situation where I have particle A in the lower state and particle B in the upper state, and particle A in the upper state and particle B in the lower state, quantum mechanics tells us that those states are indistinguishable and there is a single state. All right? And so what that says is that if we're dealing with something that is not a fermion, I can have E1, E1, E2, E2, and E1, E2, and there's only one state that counts. All right? But again, the bottom line is we do not have an equality between the system partition function and the molecular partition function raised to the nth power. All right? So just to summarize things that we've talked about so far, basically what we've shown is that we cannot use Q equals Q to the n under the circumstances where I have particles in the same state or in transposed states. So we'll just say E1 plus E2 B and A is same state as E2A plus E1B. All right? All right, so then we have to figure out ways to handle this. Okay? Well, the one thing that we can step back and say, if we know that there's a lot more states available to our system, to our particles in the system, than there are the number of particles. So I'll just throw out a number. Let's say that I have 10 million states available and I have one particle. If I put another particle in there, it's really unlikely that it's going to have the same state. So as long as I have a condition where I have lots of quantum states available compared to the number of particles, then we can conclude that it's unlikely that any two particles are in the same state. So that really means that we don't need to worry about whether our particles are fermions or not. If we know that we have enough systems to go, enough states available to the particles that they're not likely to be in the same state as another particle, then we're good. All right. Well, for an ideal gas, we need to have some criteria that tells us when I have many more states than I have particles. And that occurs whenever we have n over v, so number of particles over the volume, times h squared over 8 mkbt. As long as that number is much less than 1, then that condition is satisfied. In homework 6, number 4, you'll have an opportunity to play around with that equation a little bit, right? And then if we look at what goes into this criteria, what we can see is that if we have low n over v, and that's going to correspond to low density in terms of particles, and that, of course, will also correspond to low pressures, because if I have low particle density, then I necessarily have low pressures, right? This also occurs if I have high temperatures and high masses. Okay? All right, so assuming that we can work under the conditions where our criteria is met, then we really don't have to worry about having two particles in the same quantum state. So then the only thing that we have left to concern ourselves with is transposed levels, right? So I had intended to do the second page of a lecture quiz to talk about this one. So because we're not present, it's not going to be a quiz, but let's go ahead and talk about this. Right? So we're going to pretend that we have a system that has 4 particles, right? And it meets the criteria that there's lots of quantum states available, so that it's unlikely that any 2 of the particles will be in the same quantum state. So the way that we can talk about then is that we've got particle A, B, C, and D in quantum states 1, 2, 3, and 4. All right? Okay, so then what our goal is to determine how much we overcount if we're worried about transposing, because what we know from quantum mechanics is that this is the same as E B, E C, E D, with all of these states being 1, 2, 3, or 4. All right? So we're basically asking how many ways are there to permutate these particles into these 4 quantum states. So the way that we can do this is we can say, well, let's focus on quantum state 1. So that's the first one. All right? If each particle has to be in a different state, how many ways can I put these 4 particles in there? Well, I can put particle 1 into that first state, or 2, or 3, or 4, which means I have 4 different possibilities. Now, once I put one of the particles into that first state, right, now one's set. So I'm basically saying state 1 is occupied by particle A. So then I look at quantum state 2, and I say, well, how many ways can I now permute through the remaining particles? Well, I can put 2 in there, I can put 3 in there, and I can put 4 in there. It means there's 3 ways to do it. Okay? And then once I set particle 2, or particle B into state 2, then we ask the question, how many ways can I put a particle into state 3? All right, so A is set, B is set, and that really means I have only C and D left, so there's 2 options. All right, and if I choose to put particle C into state 3, there's only one place left for me to put the fourth particle. All right, and then we say, well, if I wanted to do all the different ways of arranging them, well, that means I'm going to need to take 4 times 3 times 2 times 1, or 4 factorial, right? That gives me the total number of ways that I can put these 4 different particles into these 4 quantum states, right? And if I generalize this and say, well, what if I have a different number? What if I have n particles and they are in n different quantum states? How many ways are there to arrange them? What is the permutations that are equivalent? That's going to correspond to n factorial, right? Okay, so basically what that says is that the redundancies is n factorial. And so what I can say is that if I want to divide out all of the overcount, I can say Q is equal to my system partition function is equal to my particle partition function over raised to the nth power divided by the overcount due to transposed states, n factorial. Right? And that's why we've been using this relationship. This works for independent, indistinguishable atoms and molecules. And that is what we've been talking about whenever we're talking about being in the gas phase. Right? Okay, so that tells us the appropriate form of the system partition function to use as long as we meet this criteria that basically tells us the number of particles is much less than the number of quantum states available. Okay. All right, now we can talk about applications of the molecular partition function. So section 3.8, molecular partition function. Or little q, right? So we're going to start with an equation that we have derived previously for system partition functions. So our average energy of an ensemble is given by kBt squared times the partial of the natural log of q, the system partition function with respect to temperature holding n and volume constant. All right. What we're going to do new here is we're going to say, well, we're going to be talking about a system of indistinguishable, independent, identical particles. So I know that Q of the system is the same as Q to the n over n factorial. So doing that substitution, I've got the natural log of the system partition functions given by n ln Q minus ln n factorial. And that I can plug in for my system partition function. That's what we've done here. All right. So let's go ahead and do that substitution. So we have kb t squared times the partial of n ln q with respect to t holding v constant minus kb t squared times the partial of ln n factorial with respect to t holding v constant. And we see that this second term goes to 0 because n factorial is a constant, right? And I know that n's a constant, so that can be pulled out front, so that will become n kb t squared, and then the partial of the natural log of the particle or molecular partition function with respect to t holding v constant. All right. And then we can say, well, the partial of the natural log of q with respect to t is going to be the same as 1 over q times the derivative of q with respect to t, holding v constant. Right? And then we see that we need to calculate or determine what the derivative of q is with respect to t. So let's do that portion. So dq dt, constant v, will be the derivative of a sum of e to the minus e sub I over kbt. That's our Boltzmann factor for the particles, and the summation over all of the quantum states gives us the molecular partition function dt. Right? And then we see, well, that's the sum. That's a derivative of a sum, which is the same as the sum of the derivatives. So that'll be the sum of derivatives of the exponential e to the minus e sub I over kbt with respect to t, holding v constant. And that leaves me with the summation, all right, over all of the quantum states. Well, we get the exponential term back, minus e to the minus e over kbt. All right. And then we need to take the derivative of the negative of the energy over kbt, and that's going to get me 1 over kb t squared. All right. And just to be clear on that, the derivative of minus e over kbt will be, oops, I left out an e sub I there, e sub I over kbt squared. Well, that's going to be a constant minus e sub I over kb times 1 over t squared negative. All right. All right. So that just shows where this entire equation comes from. All right. Okay. So this was just the derivative of the natural log of q with respect to t. So to make that consistent with the energy, I need to multiply through by kbt squared. All right. So that basically says that my average energy is going to be given by n times the summation over all of my quantum states, e sub I, e to the minus e sub I over kbt, all divided by q. Okay? All right, and because we expect that all of our particles are going to have the same average energy, it follows that n times this value has to give me n times the average energy for our particles. So E equals average particle energy and what follows from that, if we think about the statistics, I've got the energy of a particle times this Boltzmann factor over Q. That tells me that the probability of being in a particular quantum state for a particle is given by the Boltzmann factor e to the minus e sub I over kBt divided by the partition function. And that's probability particle in quantum state I. All right, now we recognize that that energy that corresponds to our particle consists of multiple terms. So that can be our translational energy, it can be our rotational energy, it can be our vibrational energy, and it could be our electronic energy. Right? So that together gives us the summation of the energy. And I can write my Boltzmann factor, e to the minus E over kBt, in terms of this summation. Right? And we previously have shown, and because of the nature of exponential function, that this is going to be the product of the Boltzmann factors for each of the different energy modes. So this will be e to the minus E translational over kBt times e to the minus E rotational over kBt times e to the minus E vibrational over kBt. And my last term, e to the minus E electronic over kBt. All right. Okay, and then we can put that all together in a grand equation that basically tells us that our particle partition function, which is a function of v and t, can be written as the product of a translational partition function, a rotational partition function, a vibrational partition function, and an electronic partition function. So each of those are defined. There's my translational, rotational, vibrational, and rotational. And that also means that I can talk about the probability of being in a particular quantum state with respect to the translational state, the rotational state, the vibrational state, the electronic state. And that's all summarized in this, right? And that means we can break it into smaller parts. So if I'm interested in knowing the probability of being in a particular translational state, I take the Boltzmann factor for that translational state over the partition function for translation. Similarly for rotation and vibration and electronic. All right? And that, of course, also means that I can calculate separately my translational, rotational, vibrational, electronic particle energies on average using a generalized equation where we have the energy of a particular mode. So it could be translational mode, rotational mode, vibrational mode, etc. And that's going to be given by our summation of the energy of that mode times the Boltzmann factor over the partition function. All right. Now, what we've shown previously is that when I take that summation, I can do a manipulation of statistics, and that turns out to tell us that kBt squared times the partial of the natural log of our partition function for a given mode with respect to t, holding the v constant, gives me the energy of that mode. All right, we're going to skip this next part until lecture tomorrow. We'll come back and fill that in. But for right now, we'll do a quick deviation. So up to this point in time, when we've been using the molecular partition function, we've been saying we're taking a summation, e to the minus beta times the energy of each quantum state. And our index, I, has been over quantum states. And we want to point out something and just remind ourselves of a few things. We know that a quantum state corresponds to a specific state of the system or of the particle and a specific wave function. We also know that different states can have the same energy. This gave rise to our concept of degeneracy. And what we've previously pointed out is that if we have different quantum states that have the same energy, we say that they are in the same level. So the in same energy level. So we also, therefore, can define a partition function not in terms of the quantum states, but in terms of the energy levels. So in doing that, it's going to look very similar. I still have a summation. I'm going to use J as the index this time, and we'll indicate that we're summing over levels rather than quantum states by indicating so. Right? We still have our Boltzmann factor, e to the minus beta e sub j. Right? But what we need to do now is just remember, well, if I have degenerate states, that means there's going to be more than one state that's in a given energy level. So I need to include the degeneracy of that state. Okay? All right, so for an example, we saw back in chapter 1 that we could determine what the energy levels for rotation are, right? And we didn't emphasize this at the time, but each of those energy levels has 2j plus 1 degenerate states, right? And so if I want to do the partition function for it, I need to take that into account. So I'll write the summation over j equals 1 over levels, the degeneracy 2j plus 1, then times my Boltzmann factor, e to the minus beta, and then the energy, h bar squared over 2I, j plus 1. All right. And so if j is equal to 0, I've only got one entry because the degeneracy is 1. But if j equals 1, the degeneracy is going to be equal to 2 times 1 plus 1, or 3. So there'll be 3 Boltzmann factors, each associated with a unique quantum state. All right. So that's where I think we'll leave it for today, and look forward to seeing you guys tomorrow. Have a good one.